Plasma nitriding is one of the advanced surface engineering processes used to increase surface hardness, wear resistance, and service life of metallic components. Compared to conventional gas nitriding, this technique operates at lower temperature and allows precise control of nitrogen diffusion and is particularly advantageous for sensitive or porous compounds such as sintered material. Plasma nitriding furnaces are generally classified into two types: cold wall furnaces and hot wall furnaces. In a cold wall furnace, the chamber walls are typically water cooled, so there is almost no heat transfer from the wall to workpiece. All the thermal energy required is generated by ion bombardment from the plasma. To reach the desired temperature, relatively high surface current densities are necessary. This can result in the so-called edge effect, where corners and sharp edges become overheated, leading to local tempering or distortion. Limitations: in cold wall furnaces, the higher current density required may cause localized overheating on edges and corners. Small and delicate parts are more sensitive to local tempering or distortion. For large-scale industrial components, these limitations are less critical, and using cold wall furnaces more economical. For complex geometries, the edge effect may result in non-uniform plasma distribution. In a hot wall furnace, heating elements are embedded into the chamber walls in addition to the plasma. These elements provide a more uniform background temperature, meaning less heating is required from the plasma itself. As a result, process control is more stable and precise, since temperature distribution and nitrogen diffusion can be regulated more effectively, minimizing the risk of hotspots. Process steps include evacuation of chamber using vacuum pumps, introduction of an active gas mixture, typically nitrogen plus hydrogen or ammonia plus hydrogen in defined ratios, application of a high voltage between the workpiece, cathode, negative, and the chamber wall, anode, positive, ionization of nitrogen atoms, producing a plasma that appears as a violet glow around the workpiece. Cleaning of the surface is critical in plasma nitriding. Any contaminants such as grease, oil, fingerprints, or oxide layers can hinder uniform nitrogen diffusion. A key advantage of plasma nitriding is the presence of a plasma sputter cleaning stage prior to nitriding. During this step, the workpiece surface bombarded by energetic ions, which remove passive film and oxide. For example, stainless steels are normally resistant to nitrogen diffusion due to their passive layer. But in plasma nitriding, this resistance is eliminated, allowing a greater case depth compared to other nitrogen methods. The typical temperature range for plasma nitriding is 400 to 600 centigrade, and the process temperature is usually selected about 30 to 50 centigrade below the tempering temperature of the steel. This prevents core softening and avoids unwanted tempering of the material. Therefore, prior to plasma nitriding, the workpiece should be fully heat treated, machined to final dimensions, and stress relieved. Otherwise, residual stresses may be released during the process and reducing dimensional accuracy of the final component. Alloying elements such as chromium, aluminum, molybdenum, and vanadium form stable nitrides, which increases surface hardness and wear resistance. Most suitable material for this process among the material are the nitro-alloy steels, specified in ASTM standard under the 1.85 series. These steels are specifically designed to respond effectively to nitrogen processes, especially plasma nitriding, due to their high content of nitride-forming elements. The advantage of plasma nitriding is lower temperature compared to the gas nitriding, which reduce distortion and improve dimensional accuracy. Environmental friendly, less pollution and fewer hazards. Simplified masking. Nitrogen diffusion can be restricted in certain area using simple mechanical masks suitable for pores and powder metallurgy parts. Nitrogen penetration can be precisely controlled by adjusting plasma parameters and pressure. Sputtering stage cleans the surface and enhancing nitrogen penetration, especially in stainless steels.
Thank you so much for your attention. I hope you found this video useful. Comment your questions and subscribe for more tutorial videos.